Hello everyone, today we will discuss another follow-up question from the house robber. LeetCode algorithm problem 337, house robber 3. First, let's see the description of the problem. The thief has found himself a new place for his thievery again. There's only one entrance to this area called root. Besides the root, each house has one and only one parent house. After a tour, the smart thief realized that all houses in this place form a binary tree. It will automatically contact the police if two directly linked houses were broken into on the same night. Given the root of the binary tree, return the maximum amount of money the thief can rob without alerting the police. Okay, the difference for the new problem and the original house robber problem is in the old house robber problem, the houses are linked as a line, but now the structure for the houses is a binary tree. Okay, let's see our solution for the old house robber problem. If houses are arranged in a line, we use DP array to store the best solutions for each smaller scaled sub problem, which is DPI equals the max 1 from DPI minus 2 plus current value for the house I, and the best solution for the houses from the leftmost until house I minus 1. However, if the houses are arranged in a binary tree, things are much more complicated. But the algorithm is also similar. We need to calculate the larger one from the situation if we rob the current node or if we will not rob the current node. Okay. In the old problem, we use array. In Python, we use a list to store the results for smaller scaled subproblems. However, for the binary tree structure, we will use two hash maps to store the results for smaller scaled subproblems, which is the best solution for fewer nodes. Like for this binary tree, the best solution for these two nodes will be a smaller scaled subproblem of the entire large problem. Okay, let's see these two hash maps. The first one, we use a Python dictionary to store the results for the nodes that we will rob. And in this dictionary, we have k value pairs, and for each pair, the k is the current node, and the value is the current node value plus the total largest money the robber can rob from the nodes in its subtrees. And similarly, for the not rob saved dictionary, the key is the current node and the value is the total largest money the theft can rob from nodes in its subtrees. Here we don't have the current node value because we don't want to rob this node. Okay. And instead of a single line function in our old solution for the easier house robber problem, we use a much more complicated recursion function to get the results for the max rob and the not rob. And we use two parameters in the recursion function. The first one is the current node, and then the second one is a Boolean variable parent robbed. The parent robbed is whether the parent node of the current node is robbed or not. There are two situations. If the parent robbed is true, which means the parent node of the current node is robbed and we cannot rob this current node. So we only need to calculate the solution if we don't rob this current node. And the second situation is if the variable is false, which means the parent node of this current node is not robbed. Then we need to calculate the best solution if we rob this node. Also, we need to calculate the solution that we don't rob this node. And then we will compare those two situations and find a larger one to return. Okay, then we will go into the recursion function and see the details of each situation. Firstly, let's say the first situation, if the parent node is robbed. If the parent node is robbed, we will not rob this current node. So firstly, we check whether the current node is in the dictionary not rob saved. If it is in the dictionary, which means we will already calculate the best solution before and stored in the hash map. So we just need to directly return the stored value linked to the current node as the key. And we don't need to calculate the best solution for this situation again. However, if the current node is not in the dictionary, which means we didn't calculate the situation for current node before, so we need to calculate in this iteration. And because we don't need to rob this current node, so we will use this situation, not rob dictionary situation. So which means we only need to consider the best solution for the largest money we can rob from the children nodes in the current nodes subtrees. So we have the recursion function go into the left subtree of the node and pass the false as the Boolean variable for the parent rob because we don't rob this current node. So for the left child node for the current node, its parent, which is the current node in this iteration, will not be robbed. So the Boolean variable should be false. Similarly, we have recursion node.write false. And then we plus these two and get the final result for this situation. Then we store the results in the not rob saved dictionary. And then the node is the key and the result is the value for the key. And then we return the current result. For the second situation, if the parent node of the current node is not robbed, the situation is more complicated. We need to calculate not only if we don't rob this current node, but also we need to rob this node. Okay, firstly we check if the current node is in the rob saved dictionary. If it is in the dictionary, which means we've already calculated this situation before, and we just return the value we stored in the dictionary. And if not, we need to calculate in this iteration. So if we want to rob this current node, the best solution is to add up the value of the current node and then the recursion result from its left subtree, and the recursion result for the right subtree of the current node. And if we decide not to rob this node, then we only use the result of the recursion for the left subtree and then the recursion result for the right subtree. And then we compare these two plans and get the larger one as the result. Then we save the final result for this situation to the rob saved dictionary, and then return the current result. Okay, we discussed all of the cases, and then from the very beginning, we just pass the root at the current road and pass false as the Boolean variable. In this way, we will solve the entire large problem. Okay, let's submit our solution. Yeah, it's success. Okay, we just finished this problem, and we will discuss the time and the space complexity. For the time complexity, we have O(n) because we traverse the entire binary tree only once. And the space complexity, we also has O(n) because we need to store the two hash maps, and because of the hash maps, we have the space complexity as O(n). Yeah, that's all for today's discussion. Thank you so much for your time. Bye bye.